Welcome back, everyone. In 2026, artificial intelligence development is defined less by sudden breakthroughs and more by consolidation of capabilities that already exist. The year represents a transition from experimentation to normalization. In this transition, systems previously tested in limited settings now operate in routine use. This shift marks a change in how artificial intelligence is treated. Systems that once appeared unstable or narrowly impressive now execute tasks repeatedly without failure during everyday operation. Artificial intelligence stops being treated as a product and starts being treated as infrastructure. As infrastructure, artificial intelligence runs continuously in the background, rather than waiting for deliberate activation. This change does not indicate a dramatic advance in intelligence. Instead, platforms raise uptime and connect artificial intelligence to more software paths. Artificial intelligence systems now run inside software and devices by default. Users no longer trigger artificial intelligence through explicit commands. The defining condition of 2026 is not surprise. The defining condition is whether artificial intelligence runs quietly and produces consistent outputs at scale without supervision. The development path leading into 2026 is shaped by limits that are already visible. One limit appears in model scaling. Training larger models now produces smaller gains than before. These reduced gains weaken incentives to increase parameter count alone. Another limit appears in hardware. Hardware constraints slow raw scaling. These constraints cap how much computation engineers can deploy efficiently. A third limit emerges during deployment. Deployment friction exposes weaknesses that benchmarks often miss. One example is inconsistent output under real workloads. Developers respond by narrowing focus. Developers select tighter operating bounds so systems produce predictable outputs. Artificial intelligence development in 2026 follows engineering discipline rather than research spectacle. Engineers design systems to fit existing operational environments. In this approach, systems route outputs into established workflows instead of replacing workflows. Progress measurement also changes. Teams measure progress by how consistently a system produces correct outputs under real operating conditions over time. User interaction with artificial intelligence systems changes in specific ways. One change affects how users give instructions. Prompt-driven interaction does not disappear. Prompt-driven interaction loses dominance as systems read contextual signals instead. Another change affects how systems respond. Artificial intelligence systems read state and history instead of relying on explicit commands. They include prior actions and current conditions rather than isolated requests. This behavior reduces the number of instructions users must issue. Reduced instruction count lowers the skill threshold required to obtain useful assistance. The result is not more expressive output. The result is assistance that produces consistent responses aligned with ongoing tasks. Artificial intelligence becomes something people work alongside, rather than something people operate directly. Please subscribe. In 2026, bounded agent systems move from demonstration to routine use. Bounded agent systems are not general problem solvers. These systems execute narrow tasks within explicit limits. Explicit limits define which actions the systems can perform. Operation follows a repeatable pattern. A typical agent scans a defined environment. The agent selects one action from a fixed set. The agent executes one step. The agent checks the result before moving to the next step. Result checking prevents drift because incorrect outputs stop further action. Step-level checks limit error accumulation over time. A major developer based in San Francisco deploys bounded agent systems inside constrained environments such as document processing pipelines and scheduling systems. Human judgment is not replaced by these systems. The systems transfer repetitive transitions between tools without interruption. The value of these systems comes from persistent task execution rather than creativity. In 2026, a significant shift emerges in how artificial intelligence workloads are distributed across hardware. Hardware alignment becomes a dominant concern in AI development. Instead of defaulting to centralized execution, engineers now decide where computation runs. Model designers carefully shape models around memory access patterns and latency budgets, which determine how quickly data moves through a system. This approach changes how engineers train and run models. Smaller models execute locally, close to the user or device, while larger models operate remotely within centralized systems. Engineers split tasks across these locations without the user noticing. This strategic placement not only shortens response times, but also reduces energy use per task by running computations in more efficient locations. Model designers now prioritize efficient parameter usage over sheer size. Architectures are designed to degrade gracefully when resources are constrained, rather than failing outright. Within this environment, domain-locked intelligence becomes increasingly prominent. These systems are trained and deployed within narrow professional contexts rather than across general knowledge, and this constraint significantly shapes their behavior. Domain-locked systems are adept at parsing formats and detecting failure modes specific to a particular field. For instance, the structure of logistics data differs from the structure of software test results, and a system trained for logistics will produce different outputs than one trained for software testing. It's the constraint differences and error patterns that cause this divergence. A major research organization based in London focuses its development on systems that operate under strict evaluation conditions. These systems suppress open-ended dialogue, emitting rule-bound outputs instead. This specialization reduces error rates and limits unsafe outputs. Broad generalization does not occur in domain-locked systems, leading to higher reliability and stronger error handling within their defined scope. As artificial intelligence becomes embedded in operational systems, regulatory pressure increasingly shapes system design. Regulatory pressure alters how engineers assemble systems. Compliance requirements require systems to record inputs and outputs. Recorded inputs and outputs allow review after execution. Logging does not make systems interpretable. Logging makes systems auditable during inspection. Developers respond by designing modular systems. Modular systems isolate responsibility so reviewers can inspect components independently. An enterprise software firm based in Waldorf integrates artificial intelligence into production environments with traceable execution paths and bounded authority. These architectural choices slow feature rollout because additional controls are required. These controls increase institutional trust. Artificial intelligence systems that cannot be inspected struggle to gain adoption in regulated environments. These technical shifts also change how human work is structured. Human skill requirements shift as artificial intelligence becomes normalized. Multiple disciplines are affected by this shift. Writing focuses on intent specification rather than sentence construction. Systems generate draft text during execution. Programming focuses on system design rather than syntax recall. Automation generates routine code segments. Analysis focuses on framing problems rather than calculating results manually. A media technology company based in Tokyo applies artificial intelligence systems inside production workflows. Human direction remains central during this process. Execution shifts to automated systems. People who adapt to directing systems gain efficiency by concentrating on decisions. People who resist automation retain relevance but lose speed. Labor impact remains uneven. Change unfolds gradually over time. Artificial intelligence amplifies existing competence rather than replacing it outright. Despite these changes, several outcomes do not occur in 2026. Perspective is shaped by these absences. Artificial general intelligence does not emerge. Artificial intelligence systems do not generate independent goals. Most failures remain mundane. Data quality issues or integration errors cause these failures rather than novel behavior. The primary change involves failure location. Failures now occur inside essential systems rather than experimental tools. An aerospace manufacturer based in Toulouse deploys artificial intelligence inside design and simulation environments. Verification layers intercept errors and block downstream propagation. Engineers treat artificial intelligence as a component within larger systems, rather than as an autonomous actor. Taken together, the most important characteristic of artificial intelligence development in 2026 is normalization. Normalization defines the overall trajectory. Artificial intelligence becomes part of the background of digital systems. Artificial intelligence no longer appears as a visible feature. Artificial intelligence routes decisions and outputs quietly and persistently. Removal would feel disruptive because dependency has formed over time. Progress measurement shifts toward uptime and integration depth rather than novelty. Dramatic change does not define this transformation. Durability defines the transformation instead. Retreat does not occur once this level of embedding is reached. Artificial intelligence becomes part of the environment in which future systems are built. Thank you very much for watching. Please like and subscribe.